According to me, it is perfectly fine. It is absolutely fine. So come on guys, share it with your friends. This is the GATE AIMER'S 2023 series where we are discussing some important concepts of every chapter. Every day I am taking one chapter. Okay, every day I am taking one chapter of communication. Like in the first chapter, we discussed about the amplitude modulation. In the second class, we discussed about the angle modulation. In the third session, we discussed about the random variables, and now we are going to discuss about the random digital communication, where I told you that we are actually going to discuss about the band pass sampling. So if it is clear to all of you, then please share the session with your friends so that the maximum students can come and take the advantage of the session. Quickly share it with your friends. Yes, good evening Ravi. So I have seen that many of you are now still joining. So share this session with your friends in the telegrams. There are different telegram groups you might be having. So share this session to your friends also. So let me also share with other places. Okay. So yeah, so I am also sharing. You guys can also share. Then we will start the session very quickly. So before starting the session, let me introduce myself. So this is Saket Verma, and I have done MTech from IIT Guwahati. I am having more than 12-year teaching experience. I have cracked the different PSU exam as well, and I teach the subjects electromagnetic theory, communication system, advanced communication system, and signals and system. So these subjects will be very important for you if you are a core ECE students. Yes, good afternoon, Aninday, Chinmay. So, still people are joining, I guess. So, as I told you that this is the GATE AIMER series where we are discussing the GATE free crash course on the YouTube, and it has been started from 1 month ago. So, if you have not taken the advantage of this series, then you can go into the playlist and you can find the lectures of the different faculties from the different subject. And as I told you that this will be beneficial for you. Why? Because we are discussing only the important topic in this particular series. And there is a GATE scholarship test also, which will give you the up to 90% scholarship test if you are a scholarship. If you are preparing for the GATE 24, then you can get up to the 90% scholarship. The test is on 24 December, that is Saturday, at 8 p.m. and you can register yourself in this particular scholarship test, and you can take the maximum discount in the course. And now there is a GATE and ECE test series also going on. GATE and ECE test series is also going on here, and you can get the unlimited access to the full length mock subject wise test. Link is given in the description. So everything you are looking for, the each and every requirement is having in your description. You can go in the description and you can check the links, and you can register yourself which is of your interest. So in the test series, we will be covering the 60 plus test, detailed mock test, virtual scientific calculator, and these questions are curated by the experts, all India mock test, and 4,000 plus questions you will be practicing. So this is bandpass sampling. Okay, we are starting the bandpass sampling. Yes, Dreamer also has joined. So now we are starting the bandpass sampling. See, in the low pass sampling, you know that if there is a low pass signal, then we can recover the signal from its samples if we take the samples at the rate of fs greater than equal to 2 fm, right? Which kind of signal you call it as a low pass signal? So yes, Hemant, good evening. So this type of signals we call it as a low pass signal, right? This is nothing but a low pass signal. The signal which is centered about origin is called the low pass signal. It is band limited to FM, and it is extended up to minus FM. So this is the spectrum of a low pass signal, So to recover the signal from its samples, the sampling frequency must be greater than equal to twice of Fm. This is our Nyquist criteria or sampling theorem. So what will happen if the signal is band limited, not exactly band limited, if what will happen if the signal is centered other than 0? Okay, when the signal is centered other than 0, like it is centered at some frequency f naught. Okay, it is centered at some frequency f naught, then we will have some lowest frequency, we will have some highest frequency, and it is centered at f naught, or for simplicity you can write fc also, because most of the time we used to take fc. So let's take fc. So this type of signal is called band pass signal, a signal which is centered around other than 0 frequency, a signal which is centered other than 0, then its sampling frequency we can calculate. There are multiple ways to calculate the sampling frequency. One way is it is also greater than equal to 2fh if we talk about the Nyquist rate. Okay, if we say about the Nyquist theorem or Nyquist rate, then fs is equal to 2fm and fs is greater than equal to 2fh, we can say. But bandpass sampling is also called undersampling. Why we call it as undersampling? That we have to understand what is the spectrum inversion, that we have to understand, and what are the problems which are related with these bandpass signal that we have to solve. Okay, so according to the statement, it states that a signal having frequency component between fh and fl as shown in the diagram, if it is having the frequency component between fh and fl, then the signal is occupying a particular band. Because it is lying between fh and fl, then the signal will occupy a particular band, and that is lying between fh and fl. So in this type of signal can be completely reconstructed by its samples if the sample is done significantly lower than 2fh or sometimes equal to 2fh. So what we are saying, that it is not necessary to have fs greater than equal to 2fh. We can also take fs less than 2fh. So now the sampling frequency, we will say that it is less than or equal to 2fh, and because according to the Nyquist theorem or according to the sampling theorem, when the fs is equal to 2fm, we call it as a Nyquist rate, and it should always be greater than 2fm. And if the sampling frequency is less than 2fm, in case of low pass signal we call it as undersampling. But here we are saying that the band pass signal can be recovered from its samples if you take the sampling frequency less than equal to 2fh. That means even if you undersample the signal, you will be able to recover your message signal. Okay, so this is the first point. Now the second point says the bandpass sampling is used to sample a continuous bandpass signal that is centered about some frequency other than 0. Bandpass sampling not only reduces the speed requirement of a to D converter, but also reduces the amount of digital memory necessary to capture the given interval of continuous signal. So here we are saying that the bandpass sampling reduces the speed requirement of A to D converter, and also it requires less memory because it reduces the amount of memory to store. Okay, so that is also reduces. So speed also reduces and memory also reduces in case of bandpass sampling. Bandpass sampling is also known as harmonic sampling, sub-Nyquist sampling, and undersampling. So we call it as fs less than equal to 2fh. So 2fh is the Nyquist sampling rate, and if the sampling frequency is less than 2fh, then we used to call it as a undersampling. So we can sample the bandpass signal with the sampling frequency less than 2fh, which is called undersampling. In the bandpass sampling, we are more concerned with the signal bandwidth rather than its highest frequency component. So we are more interested in the bandwidth of the signal. What is the bandwidth of the signal? Which is FH minus FL. So this is the bandwidth of the signal in which we are more interested rather than the highest frequency itself. Now the next point is the bandpass sampling performs digitization and frequency translation in a single process. That is why it is called as sampling translation. Okay, so bandpass sampling is also known as sampling translation because it performs the operation simultaneously. Okay, now let's take one example of bandpass signal. This is a bandpass signal. This bandpass signal is having the bandwidth 5 kilohertz and its spectrum is shown in below figure. It is centered about 20. Okay, it is centered about 20. That means the carrier frequency is, or the center frequency is 20. The bandwidth is 5. That means it will be ranging from 17.5 to 22.5. So the bandwidth is calculated from highest frequency minus lowest frequency, and this is your bandwidth which is given as 5. Okay, this is the bandwidth which is given as 5 kilohertz. So let us take this particular component as P and this component as Q. So this is our information. This is our information. This information we want to sample. Okay, so our complete information lies in the set of two components P and Q. So whenever we want to recover our message signal, we want to receive one P and one Q. Okay, are you getting this point? Because this is our information and this information we want to transmit using the digital communication, using the digital techniques. So if you want to transmit the information, you are converting this into a binary data. To convert into binary data, you are performing some operation like sampling, quantization, and coding. So the first step is sampling. So to sample the information, we will use either bandpass sampling or low pass sampling. Because our information lies in the bandpass signal, so our complete information lies in a one pair which is P and Q. So whenever we want to recover our message signal, we will say if we get the P and Q together, we will call it as that our information is recovered. So tell me, up to this point it is clear or not? When you will say that your information is recovered? When you get the set of P and Q. When you get the set of P and Q. And our information is lying between 17.5 to 22.5, and in the negative side minus 17.5 to minus 22.5. We know that whenever we sample the signal, we get the replica of the signal. Okay, we get the replica of the signal because like when we sample the low pass signal, suppose this is the signal MT and the MT is having the Fourier transform M of F, then after sampling, okay, then after sampling we get the MST. After sampling we get MST, which will have the Fourier transform Fs multiplied with n is equal to minus infinite to infinite m of f minus nfs. So m of f minus nfs gives, okay, this term gives original spectrum as well as its replica. So original spectrum we get, okay, original spectrum, that is our m of f for n equal to 0, and number of replicas, okay, number of replica. So the replica are also having the same information, but which you want to recover is important and how you can recover is important. Okay, Aninder and Dreamer and all of you, please tell, is it clear? Okay, so now we have the message signal which is having a pair of component P and Q centered at 20 and the highest frequency is 22.5. So according to the Nyquist rate, this is the Nyquist rate. Nyquist rate is nothing but a twice of highest frequency. Okay. Nyquist rate is nothing but a twice of highest frequency. Highest frequency is 22.5. So 2 into 22.5 is 45. So if I sample with the sampling frequency 45, then the Nyquist rate will be, then the signal component will be looking like this. See, this is the M of F minus NFS, and for n equal to 0 we get M of F, and for n equal to 1 we get M of F minus Fs. So this is the component which is our original spectrum, that is M of F, which is having the component P and Q. Okay. So that is the point that we are going to discuss, and in that if you will watch this lecture completely, you will understand that when you have to apply Fs equal to 2Fh and when Fs is less than 2Fh. Okay, so we know that this is our spectrum which is going to give, we are going to get this after sampling. Okay, we are going to get this type of signal after sampling. So after sampling you will get M of F minus NFS multiplied with Fs also, but we are not bothering about the amplitude. Now when we put n equal to 0 we get M of F. So this spectrum we will get for n equal to 0, which will give us original spectrum. Now for n equal to 1 we are getting M of F minus Fs. That means this spectrum has to be shifted by 45 because Fs we have taken as 45. Okay, Fs we have taken as 45. So when you shift this particular spectrum by 45 towards right, so towards right means you will add 45 to the whole axis. When you will add 45 to the whole axis, you will get 67.5, and here when you will add, you will get 22.5. So this point of P, this component which is P, it will start from 22.5. That means this one is P, and this Q will end up to 67.5. So this is Q. So this P and Q will be shifted in the right hand side, and when we put n equal to minus 1, when we put n equal to minus 1, suppose I put n equal to minus 1, then I will get M of F plus Fs. So M of F plus Fs means you have to shift towards left. So to shift towards left, what you can do, you can subtract 45. So when you will subtract 45, this will be minus 67.5. So this is this point, and this will be your minus 22.5. So this will be this point. So this Q will shift here and this P will shift here. Okay. So this is for n equal to minus 1. Are you getting this point? Tell me, are you getting this? That how we are getting this spectrum for n equal to minus 1 and n equal to 1. This is n equal to minus 1 and n equal to 1. Okay, so we are adding M of F minus Fs and M of F plus Fs. Okay. So now, because as we said that when we sample any signal, we get M of F minus. For n equal to 1, Dreamer, for n equal to 1, you have to simply shift the signal towards right. That is the delay of the signal. I hope that you know how to delay the signal. How to delay the signal, and the sampling frequency here is 45. So you have to delay the signal by 45. You have to delay the signal by 45. Are you getting? How can you shift by 45? So when you shift towards right, this will be shifted towards right. Okay, and when you will shift towards left, this is shifted towards left. So advanced operation means left shift and delay operation means right shift. Okay. Yes. Okay, got it. Now, as I said that we have to add all of them because we know that our original spectrum when we sample, then it is Fs summation over n equal to minus infinite to infinite m of f minus nfs. So we have to add all of this component. Whatever we are getting for n equal to 0, n equal to minus 1, n equal to 1, we have to add all of them. So when we add this, we will get this spectrum. See, m of f minus fs, m of f plus fs. When we add all of them, then we get, this is our original spectrum which is PQ, and this is its replica which we have shifted towards left, and this is another spectrum which we are getting towards right, that is also a replica. So this spectrum, are you able to understand? This yellow line, this P and Q for n equal to 0 is our original spectrum, and this red P and Q are its replica, and all the PQ are having our information. A set of P and Q are having our information. So if you want to recover your information, what you will use? You will use, okay, to recover the message signal, we will use a low pass filter with cutoff frequency 22.5 kilohertz. Okay. Our original information is for n equal to 0, that P and Q we want to recover. So this 22.5 in the minus sign, and this is the plus 22.5, this we want to recover because our original information, this is our original information, it is ranging from minus 22.5 to plus 22.5. So to recover that, we will use the low pass filter with cutoff frequency 22.5. But as you can see that when I am using the low pass filter with the cutoff frequency 22.5, actually I am wasting this bandwidth. Yes, this is ideal low pass filter only, and also we are wasting this particular band. Okay, this particular band ranging from minus 17.5 to 17.5, we are wasting the frequencies or bandwidth because this 17.5 kilohertz is a significant number. Any other message signal can lie between minus 17.5 to 17.5. So if any other message signal lies between these range, then our low pass filter will pass that particular message also. So along with our original information, we may get some other information also. And second thing, that we are wasting these frequencies minus 17.5 kilohertz to 17.5. We are just wasting the frequency, we are not properly utilizing. Okay, so the information can be recovered, but this is not a good design of the filter, because this low pass filter is having the high cutoff frequency, which is the 22.5, and along with that we are wasting the frequency ranging from minus 17.5 to 17.5, because there is no other component, and we don't want, actually there should not be any other information between minus 17.5 to 17.5. But suppose if it comes, then this low pass filter allows it to pass, so that will also not give us proper result. And if suppose there is no message signal, then it is okay that we will get our message signal perfectly, but we are wasting the range of the frequency. So that is why this type of design is not actually considered. Okay, so what we have to do, then, this sampling frequency 45 we had selected by the Nyquist criteria. Okay, we had selected the sampling frequency 45, that is our Nyquist rate. So we said that the bandpass sampling is also called undersampling. So undersampling means we can select the sampling frequency less than 45. So what should be the value of sampling frequency? So the sampling frequency is calculated by this formula. Okay, the sampling frequency is calculated by this formula, which is 2fc plus b divided by m plus 1 greater than less than equal to fs less than equal to 2fc minus b divided by m. And when we select the sampling frequency using this formula, we have to keep in mind that the sampling frequency should also be greater than 2b. The sampling frequency should also be greater than 2b. Okay, when whatever value f of fs you select, the fs value should always be greater than 2b. And here m plus 1 is denoted by k, and k is calculated by fh upon b, where we select the integer part only, and m is the number of replica between the original spectrum, Okay, and now the note point is, whenever the FC, that is the center frequency, is very greater than the bandwidth of the signal, it is called as the narrowband signal, and in such cases we can use the sampling frequency directly equal to 2fh, which is nothing but the Nyquist rate. So if in the question they will ask you to calculate the Nyquist rate for bandpass signal, then you can calculate the sampling frequency is equal to 2fh. Okay, and if they will give you fc very greater than b, then also you can use fs equal to 2fh. So the condition of using the sampling frequency equal to 2fh are: first, whether it is mentioned in the question that calculate the Nyquist rate for the bandpass signal, and second, if they will give you the value of center frequency and the bandwidth in such a way that the fc is very greater than b. So if this condition satisfies, then also you can use fs is equal to 2fh. So there are two cases when we use the fs equal to 2fh. If these two cases will not satisfy, and if they ask, okay, if in the question they are asking for minimum sampling frequency, okay, if in the question they are asking for minimum sampling frequency, if they will ask for the minimum sampling frequency, then we will use this formula. Okay, then we will use sampling frequency fs is given by this formula. it is not that much critical value. The order should not be same. That means like it if all are in kilohertz, then you cannot say that FC is very greater than B. If FC is in megahertz and the bandwidth is in kilohertz, then we can say that FC is very greater than B. So the order of FC and the bandwidth should not be same. The order, that means both should not be in kilohertz, both should not be in megahertz, both should not be in hertz, like that. So the order of the frequency should not be same. So around 30, 40 times very greater than, we can say, when it is very greater, like 1000 times or 50 times, like that. There is no such critical value. Now, if I take m equal to 1, okay, suppose I am looking for the minimum sampling frequency. What is the maximum sampling frequency you can take? What is the maximum sampling frequency you can take in this case? That is nothing but a 2fh. We have already written that the sampling frequency should be less than equal to 2fh. So the maximum sampling frequency we can take is, the maximum sampling frequency we can take is fs is equal to 2fh, which we have already taken as 45 kilohertz. Okay, so this is the maximum sampling frequency. Now we are looking for the minimum sampling frequency. So how can we calculate the minimum sampling frequency? So we have to use this formula. So when I substitute m is equal to 1 in this formula, so this will be 2fc plus b divided by 2, and this is 2fc minus b divided by 1. So when I solve it, I get 22.5 kilohertz to 35 kilohertz. So I can take the sampling frequency in between these range. Means there is no fixed value. If you take the sampling frequency 22.5, that is also okay. If you take fs is equal to 30 kilohertz, that will also be okay. If you take the sampling frequency 32 kilohertz, that is also fine. If you take fs is equal to 35, that is also fine. That means in this range, if you select any of the sampling frequency, you are going to get the message signal. Okay, you will recover your message signal without distortion. But we are looking for the minimum sampling frequency. So let's take fs is equal to 35. Suppose I go for the higher side. When I take fs is equal to 35 and I shift it, okay, we know that it will be shifted. Okay, we know that it will be shifted because of this formula, summation over n, m of f minus nfs. So because of this, for n equal to 0, we will get m of f, which is n equal to 0, n equal to 0, m of f is p and q, right? And when we put n equal to 1, it will be shifted by fs, and fs is 35. So when we shift it to by 35, then we will get this as p and this as q. Okay, so n equal to 1, here also we will get some component. When you will shift towards right, you will get one pair p and q here, and when you shift towards left, you will get one pair here. This is q and this is p. Okay, but we are not interested in the part of the component which is beyond 22.5. Okay, which is beyond 22.5, because our original spectrum is ranging from minus 22.5 to 22.5. So we are not interested in this part. That is why I had not drawn in the diagram. Okay, now as I said that m is equal to 1, m is equal to 1 is number of replica. So you can see that how many replica is there in between your original message signal. This p and this q is your original spectrum. This p and q is original spectrum. Okay, and in between this pq we have one pair of pq. So one pair of pq means number of replica is 1. So m equal to 1 I had taken. So because of m equal to 1, I am getting one pair of p and q between the n equal to 0 or between the original spectrum. Okay, now I can use the low pass filter. Yes, now I can use the low pass filter, and we can use to recover the component again, to recover our information, or to recover our message signal. To recover our message signal, we use low pass filter with cutoff frequency, 17.5 kilohertz. Okay, now in the previous case, when we took sampling frequency 45, the cutoff frequency of the low pass filter was 22.5. But when we take the sampling frequency 35, the cutoff frequency become 17.5. So it is quite less. It is less, but still there is a waste of frequency, because still in between P and Q there is a gap. In between the P and Q there is a gap, and which we are not utilizing, or which we are not using. So that is why this 35 kilohertz we will not use. Means we can use it, but as I said, if you use the Fs equal to 35, you are wasting the bandwidth. Now let's take the minimum side. What is the minimum side? That is 22.5. Okay, now if I take Fs equal to 22.5, suppose I take Fs equal to 22.5, then what I saw is our original spectrum is P and Q, that is at its place, but when I shift it by 22.5, this P has gone in this place and this Q has gone into this place. Yes, we can further reduce by then the 35. So as I said, when I take Fs is equal to 22.5, this P and Q we are getting around 0. We are getting around 0. Now if I want to recover it, okay, so message can be obtained by using low pass filter with cutoff frequency, of how much? Only 5 kilohertz. Now, previously you were using 22.5. Then you were using a low pass filter with cutoff frequency 17.5. But when you choose the sampling frequency 22.5, your low pass filter has the cutoff frequency 5, which is very less. And another important point is, now there is no gap between the P and Q. There is no gap. That means you are not wasting the bandwidth now. You are not wasting the frequency gap. So this P and Q you are getting exactly at 0. So with the low pass filter you can easily recover your information, because to recover your information you need a pair of P and Q. So you are getting P and Q and you are getting your information. Yes. So spectrum is inverted here because our original spectrum, okay, so our original spectrum here we can say this is our original spectrum. In the original spectrum, the P is in the left hand side and this Q is in the right hand side. Okay, so this is our original spectrum. P should be in the left hand side and Q should be in the right hand side. But now when I am sampling with the sampling frequency 22.5, I am getting my information, but P is now in the right hand side and Q has reached to the left hand side. That means they have inverted. So that is why we call it as spectrum inversion. So when M is equal to 1 and Fs is equal to 22.5 I can recover my message signal, but the spectrum is inverted. So this is known as spectrum inversion. This is known as spectrum inversion. Got it? Anyone having any doubt in this? Clear? Good. Now, can we reduce the sampling frequency further? Can we reduce the sampling frequency further? Because we had chosen m equal to 1. So we can take m equal to 2 also. Yes, spectrum inversion is not harmful, but can we reduce the sampling frequency further? That is our main question, because we are looking for the minimum sampling frequency. So can I say that this 22.5 is the minimum sampling frequency, or we can further reduce? So let's take m equal to 2. So when I take m equal to 2, the sampling frequency is further reduced, and now this fs is ranging from 15 to 17.5. And whatever frequency you will select between the 15 and 17.5, as I told you that whatever sampling frequency you select, it should always be greater than 2b. Okay, it should always be greater than 2b. So here if I choose fs, what is the value of b? The value of b is 2 into 5. So the fs should always be greater than 10. So fs should always be greater than 10 kilohertz. So whatever sampling frequency you choose, it should always greater than 10, and the value of sampling frequency should be such that the message signal should be recovered. So these two conditions we have to follow. Even if the fs is greater than 10, and if it is not able to recover our message signal, then it is of no use, because as you can see that by the formula we are getting the sampling frequency, ranging from 15 to 17.5. okay, by the formula you are getting the sampling frequency which is ranging from 15 to 17.5. So if I choose fs is equal to 12, okay, suppose I choose fs is equal to 12, then it is not lying in this range. It is not lying in this range, and this fs is equal to 12 is satisfying this criteria. fs is greater than 2b, so 12 is greater than 10, so that is correct, but it is not coming in the desired range. So that is why fs equal to 12 will not give you the proper reconstruction. fs is equal to 12 will not give you proper reconstruction, because both conditions should be satisfied. First, the sampling frequency should lie in the range given by this formula. Okay, so sampling frequency should lie in the range which is given by this formula, and also the sampling frequency should be selected in such a way that it should be greater than or equal to 2b. It should be greater than or equal to 2b. So here we choose 35 and we had chosen 22.5. Both are greater than 10. Hence, both the frequency are valid sampling frequency. Both the frequency are valid sampling frequency which can reconstruct our message signal properly. But here if I choose sampling frequency which is beyond this range but greater than 2b, is not a valid sampling frequency. It will not give you perfect reconstruction of information. Okay, so now in this case again I am taking the maximum frequency first, which is 17.5. so if I take the 17.5, then this is our original spectrum, which is p and q, and this is its replica, because m is equal to 2. Okay, because m is equal to 2, number of replica will be 2. So you can see that in between p and q we have this p and this p, and this is q and this is q. So two pair of p and q are coming. So between the spectrum, two pair of p and q are coming. Hence the m equal to 2. So number of replica is 2. That means there are two pair which is coming between the original spectrum. Now here you can see that in this diagram, when I take the fs is equal to 17.5, after shifting, the shifting I am not explaining because you know how to shift the signal. So after shifting I am getting this type of signal. obviously there will be more component in the right hand side of this Q and in the left hand side of this P, but we are not interested in that. Okay, so here you can see that this spectrum P and Q are centered about origin. So here we can use the low pass filter. So message signal can be obtained by using low pass filter with cutoff frequency 5 kilohertz, with cutoff 5 kilohertz, right? And also no spectrum inversion has occurred because the P should be in the left hand side and P is still in the left hand side, and our original information was having Q in the right hand side and it is having the Q in the right hand side, so no spectrum inversion has occurred. Are you getting this? Yes. Now, if I choose Fs is equal to 15, you can see that this is P and this is Q. This is our original spectrum and its replica are this is Q, this is P, this is Q, this is P. So again, if you observe, we can recover our information by using the low pass filter with the cutoff frequency 7.5, but there is a gap between the P and Q. So again, we are not properly utilizing the filter, and the spectrum inversion is still not there because the P is still present in the left hand side and Q is still present in the right hand side. So no spectrum inversion here also. No spectrum inversion in this case also. No spectrum inversion. Okay, and Fs is equal to 17.5 is more efficient because there was no gap between P and Q, right? Here we have to use the low pass filter with the cutoff frequency. Okay, here we have to use the low pass filter with cutoff frequency 7.5, which is not utilizing the bandwidth or the range of frequency properly. There is a gap between P and Q which is not desirable practically. In the low pass filter, when we use the low pass filter, we don't want any spectrum to be left near about origin. Near about origin, there should not be any gap. So it is not a desirable characteristic of a low pass filter. Hence, this is not considered. So obviously 17.5 was better. So this process is continued till Fs greater than 2F. 2b, it should be 2b. Okay, it should be because m equal to 1 I have substituted, m equal to 2 I have substituted, now m equal to 3, m equal to 4. Such a long process we cannot apply in the question, in the examination. We are learning the concept, but this cannot be done in the examination. So what we have to do in the exam, that I will tell you. Now after this, when I substitute m equal to 3 again, so obviously the number of replica will be 3 now. The number of replica will be 3 now. Okay, when I put Fs, when I calculated with m equal to 3, I got the Fs greater than 11.25 and less than 11.6, which is still satisfying the criteria of Fs greater than 2b. Which is still satisfying the criteria of Fs equal to 2b. Okay, that means this 11.25 can also be chosen as a sampling frequency. So when I take Fs is equal to 11.25, this is P, this is Q. Okay, this is our original spectrum. This is P, this is P, this is P. Okay, and this is Q, this is Q, and this is Q. So we have got 3 replica. Okay, so 3 pair of information we are getting. So 3 replica we are getting because the number of replica is 3 because we have taken m equal to 3. So when I take 11.25 as a sampling frequency, what I saw is we are getting our one pair of P and Q near to origin. We are getting one pair of P and Q near to origin. Okay, near to origin we are getting one pair of P and Q. Right? So one pair of P and Q we are getting. So replica is repeated after every Fs interval. Spectrum inversion is occurring here. Okay, spectrum inversion is there, but as we said that spectrum inversion is not a problem. Okay, spectrum inversion is not a problem in the receiver. Okay, this is just we are looking for the lowest sampling frequency. So 11.25 is the lowest sampling frequency we are getting with the spectrum inversion. So Fs is equal to 11.25 is the optimum sampling frequency. Okay. So now what will happen when I put m equal to 4? So when I put m equal to 4, the inequality will be Fs should be greater than 9 but should be less than 8.75, which is not possible. This inequality does not hold. This inequality does not hold because how it is possible to have greater than 9 and less than 8.75? Okay, it does not hold. This inequality does not hold, right? So Fs, because this inequality does not hold, and also Fs is not greater than 2b in this case, because if I select 9, if I select 8.75, then both of them are not greater than 2b. Hence, this both the equations are not satisfying, so overlapping will occur. That means aliasing will occur. When I choose m equal to 5, suppose I increase the value of m further, then also this inequality doesn't hold. Then also Fs is not greater than 2b. Okay, it is not greater than 2b. Hence, this is giving us aliasing effect. So this is giving us aliasing effect. This is our original spectrum P and Q, and all the signals in between them, all the replica in between them gets overlapped. Okay, so this is also not considered. So now if I conclude it through the table, then for m equal to 1, we have got 2fc plus b upon m plus 1, which is ranging from 22.5 to 35. So in these two frequency, which one was optimum? We said 22.5 is giving us original spectrum with the spectrum inversion. When we choose m equal to 2, this is ranging from 15 to 17.5, but in both of these two values, 17.5 was giving the spectrum near to origin. So we said that this 17.5 will be better sampling frequency. But when we choose m equal to 3, we still get the sampling frequency which is valid sampling frequency, which is satisfying the Nyquist criteria. So 11.25 and 11.67. So in between these two, means 11.25 and 11.67, out of these two, the optimum one was 11.25, because this 11.25 was giving the spectrum. This 11.25 was giving the spectrum exactly at origin, which is our practical desired characteristics of low pass filter. So we will select the minimum sampling frequency as, so we will calculate when we calculate this, so we will select the minimum sampling frequency as 11.25 kilohertz. Okay, so that is the minimum sampling frequency. So 45 is also okay. 45 is also okay. 20 in between 22.5, in between 22.5 to 35 is also okay. In between 15 to 17.5, any value, all will be able to reconstruct your message signal. Okay, all the three case, m equal to 1, 2, 3, this complete range is able to recover your message signal. But what is minimum sampling frequency? The minimum sampling frequency is 11.25. Okay, the minimum sampling frequency is 11.25. Is it clear? Why we are not choosing m equal to 4 and m equal to 5? It is clear because it is not satisfying the inequality and it is also not satisfying the condition of fs being greater than 2b. So these are the two different conditions. Now, one more thing that you might have read here, to avoid the spectrum inversion, the integer m will be always even. It should always be even. Okay, so when we have taken m equal to 5, not 5, let's take m equal to 3. When we had taken m equal to 3, you can see that the p has shifted towards right and q has shifted towards left. Even though the sampling frequency is minimum, but the spectrum inversion was occurred. So when we choose m equal to 2, when we choose m equal to 2, whether it is a 15 kilohertz or 17.5, this P is still in the left hand side and Q is still in the right hand side, same as the original spectrum. So in both the case, whether I choose 17.5, this P is in the left hand side and Q is in the right hand side, or I choose the 15 kilohertz, P is in the left hand side and Q is the right hand side. So this is the condition of even integer. So when I choose even value of m, when I choose even value of m, spectrum inversion will be avoided. Okay, so to avoid the spectrum inversion, m should always be an integer number. Okay, now obviously one thing should be coming in our mind that we cannot do this in examination. So how can we calculate? So here you can see that this is the first case. This is the first case. Here we are having the center frequency. Okay, here we are having the center frequency. What was that center frequency? 20. Yes, center frequency was 20 and the bandwidth was 5 kilohertz. Okay, that is our original bandpass signal. This was given to us. So here you can see that FC is not very greater than, not very greater than B, not very greater than B. FC is not very greater than B. Okay, when FC is not very greater than B, then what we have to do? Okay, when FC is not very greater than B, so because both are in kilohertz, na? This is also kilohertz, this is also kilohertz, and the factor by which they are differ is 4 only. The center frequency is only 4 times of bandwidth. So that is not a very high value, right? So FC is not very greater than B. So in such case, you have to apply the 3-step procedure to calculate the sampling frequency. Step 1, calculate the bandwidth by FH minus FL. Okay. Step 2, calculate the value of K, which is FH upon B, in which you have to choose only integer part. Okay, that is, if suppose you calculate the K and if you get 5.7, then the value of K will be 5. If you divide it FH upon B and you suppose get 8.2, then K will be 8. So what we are doing, we are choosing only the integer part, that is 5, that is 8. So K is equal to 5 and 8. And then step 3 you have to apply is sampling frequency is equal to 2FH upon K. Okay, so these 3 steps you have to apply. So let's apply these 3 cases in the present scenario, because this is the case when FC is not very greater than B. So what is the B? B is already given, which is 5 kilohertz. What is the value of K here? The value of K is FH. highest frequency was 22.5 and the bandwidth is 5, so you are getting 4.5. So what value of k you will choose? K is equal to 4 you will choose. And what is the minimum sampling frequency? This will give you the minimum sampling frequency. Okay, this will give you the minimum sampling frequency. So what is the minimum sampling frequency? This is according to formula 2 into fh. What is fh? Fh is 22.5 divided by k. K is 4. K is 4. So when you will solve it, you will get 11.25 kilohertz. That we have already calculated in the previous discussion. So you don't need to calculate in the way I told you. You have to apply this condition. Okay, you have to check. Okay, you have to check whether the FC is very greater than B or not. And if it is very greater, then you just follow these 3 steps. Yes, this is for broadband. When FC is not very greater than B, then it is called broadband. Okay, so this is only applied for the broadband signal. Okay. Now the case 2 is when FC is very greater than B, that is your narrowband signal. Okay, that is your narrowband signal. So in this case, the sampling frequency will be equal to 2 times of highest frequency. Because it is only 4 times, Ravi, it is only just 4 times of the center frequency bandwidth. The center frequency is just 4 times of the bandwidth. So the center frequency is just the 4 times of bandwidth, so it is not greater. Okay, because it is also in kilohertz, it is also in kilohertz. So to get the center frequency, you have to multiply only by factor 4. So that is not very greater. So both are in the same order also. This is also in kilohertz, this is also in kilohertz. So that is why also we are not saying that the FC is very greater. Okay, the FC is very greater when we say when it is in the different order. Okay, when it is in the different order, like one is in the kilohertz, another is in the megahertz, one is in the megahertz, another is in the gigahertz. So in such cases, we usually say that they are very greater. Okay, so this is the 2 case, right? So actually whenever in the examination they will ask you for the spectrum inversion. Okay, whenever they will ask you for the spectrum inversion, then you have to apply the formula that I have given you for the calculation of, to avoid the, if condition of spectrum inversion, if they ask if they ask sampling frequency with or without spectrum inversion, okay, if they ask sampling frequency with or without, they may ask you for without spectrum inversion what will be the sampling frequency. They may ask you what will be the sampling frequency with spectrum inversion. Okay, so if they ask minimum, in fact I should mention minimum also, minimum sampling frequency with or without spectrum inversion, then you have to apply this formula. What was that? The formula was this one, 2fc plus b divided by m plus 1. Okay, 2fc plus b divided by m plus 1 and 2fc minus b divided by m. Okay, so note this point. Clear? Dreamer, Anindya, it is clear to you, and Dreamer also, and these three steps. So there are these three formula to calculate the sampling frequency. Understood, right? So these are the two questions which is homework for you, because we have to, I have another class at 6 o'clock, so we will do this problem sometime else. There are three problems I have shown you. You can just do the practice. This is the first question where it is asking for avoiding aliasing effect. This is another question where they are asking for the minimum sampling frequency, and this is another question where this is also asking for the minimum sampling frequency. So if you are preparing for GATE 24, then you can join our free fundamental series which is running in the app. So GATE app, BYJU'S Exam Prep GATE app, you can download and you can register yourself. And please tell to your juniors also to join this type of series. That will help them to understand whether uh, how to prepare for the GATE, whether they should prepare for GATE or not, because this is a fundamental series. Here you will come to know that which kind of question going to ask in the GATE examination. And for GATE 23, there is a rank booster series. So there are free ebooks available in the link. It is in the description. The link is given. You can go to that link and you can download the free ebook also. And there is a scholarship test on the 24th of December. So don't forget to register yourself for the scholarship test and tell to your juniors if they want a scholarship test for the GATE 2024 course, then they should register themselves in the scholarship test. Okay. So thank you for watching this session. Yes, Anindya, we will cover that in some other session for sure. Okay. So thank you again, and we will meet day after tomorrow at 4 o'clock with the information theory or the noise in digital communication, and tomorrow at 9 o'clock. Okay, tomorrow at 9 o'clock we have the PYQ series of communication. PYQ of communication we will do. Okay, so tomorrow PYQ of communication we will do at 9 p.m. So tomorrow we don't have the AIMER'S series. Day after tomorrow, that is on Saturday 4 p.m. we have the last session of the crash course. Okay, thank you. So don't forget, just set the reminder for tomorrow at 9 p.m. You have to solve this previous year questions of communication with me. Thank you.